Hello, thanks for joining us. My name is Andrew Dunkley, the host of Space Nuts. It's great to have your company, and we've got a lot to talk about. In fact, the audience is going to do the talking because we're dedicating the whole show to questions. So we've got questions about Artemis 1, dark matter, flickering stars, space-time, black holes, gravity, and terraforming Venus, which will be interesting because it's a hotbed, that place, a very, very nasty place if you set foot on it, which I don't advise. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew. How are you doing?
I am quite well, thank you, sir. And you're looking fine?
Yeah, I feel all right. Thank you. All good.
Yeah, that's good. That's good. All right. Well, we might as well just cut to the chase and start answering some of these questions because I love question episodes.
Me too.
And I know we usually do every fifth, but we've been mixing it up. Oh, boy, haven't we? So we're not waiting till next week. We're doing it today.
Just a pair of rappers we are. We're doing anything.
We are. Yeah, we just, we're not going to conform anymore. Question
right.
episode a week early. All right, let's get stuck into it. This is an ongoing story concerning a certain rocket that is still on the ground when it shouldn't be, known as Artemis 1. Ryan has a question.
Hey, Fred and Andrew. This is Ryan from Townsend, Delaware in the United States. I have a question about the Space Launch System, the SLS. The main tank is coated in that orange foam, much like the Space Shuttle's main tank was. The primary reason for the main tank being coated in foam for the Space Shuttle was to prevent the buildup of ice on the outside of it that during launch could break free and damage the fragile heat tiles underneath the Space Shuttle. But the SLS has no Space Shuttle hanging off its back. So ice breaking free from it should pose little to no danger. I'm just curious if you happen to know why the SLS is coated and painted orange like that with that protective foam. Thanks for everything you guys do. Love the podcast and can't wait to hear the answer.
Okay, thank you, Ryan. It's a good question. I think I know the answer to this one, sort of. But, safety is obviously a major consideration regardless, even with a rocket launch that's not going to have anyone on it, because in the future, Artemis will have people on board. So maybe we backtrack and talk about that particular tank that he's referring to.
Yeah, that's right. So, Andrew, that was essentially the same tank that was used exactly as Ryan says, for the Space Shuttle. The Space Shuttle had it attached to the side with the booster rockets, and the Space Shuttle's 3 engines did actually think only something like less than 20% of the work of getting the spacecraft into certainly to high altitude, because the Space Shuttle had 2 firework night boosters attached to it, solid fuel boosters, which are also used in the Space Launch System. So there's a lot of technology that has been transferred from one to the other. And I think that the fuel tank itself, which actually basically makes up the main body of the SLS rocket, it won't be exactly the same because it's got to take stresses that the fuel tank didn't have to take. But a lot of design principles have been incorporated, including that insulating foam, with good reason, I think, because the prevention of ice buildup is really important when you've got anything attached to the rocket. And in this case, you've got the 2 solid fuel boosters strapped one on either side of it. So if you had a lump of ice that clobbered one of these in a critical position, Now, it's not anywhere near as fragile as the wing of the space shuttle, and of course, that's what brought the Columbia spacecraft down when it tried to re-enter because of a penetration of the wing by a chunk of ice. So the solid fuel boosters aren't that fragile, but the last thing you want anything being hit by is a solid lump of ice. And I think that's the bottom line. That is why we still see the orange. It's not the most beautiful color. I heard another description for the color. I forgot what it was. It wasn't magnolia, but it was something like that. Very fancy.
Baby something?
Mandarin or something. It was. No, it wasn't a baby one, but it was something much more floral. It's a nice description, but of course it's orange, really. So.
Yeah, I do recall with the very first official space shuttle mission, they did paint it white for the occasion. So the first launch was the whole thing was white. The shuttle was white, the solid rocket boosters was white, and the SLS was white. But they only did it once because it was expensive, and they, wanted to show the thing off. But subsequent missions, it was that San Francisco bridge colour.
Yeah.
and here, sidebar. Do you know why the San Francisco bridge, the Golden Gate Bridge, is that colour?
It's the nearest that could get to golden, probably.
No, nothing to do with it. Nothing to do with it.
Sure
the guy who built the bridge loved the colour.
Oh, really?
That's all there is to it.
Yeah.
He just loved the colour.
Colours are really interesting in their historical context. And I'm going to throw one in as well that has no relation to any of what we've been talking about, except it's about colour. And that is the Anglo-Australian telescope, the largest optical telescope in Australia, which is not far from where you are sitting now, about 150 kilometres as the crow flies. Its colour, you might remember because you've been there and you've seen it. The tube of the tube structure of the telescope, which is not a tube, it's like an open lattice framework. Excuse me, that's white. That bit of it is the moving bit, but the mounting itself, the bit that steers the telescope around, half of it is a sort of avocado or mustardy colour, and the other half is either gravy or chocolate, depending on which you like best. But those colours were chosen by the wife of the commissioning astronomer. Ben Gascoigne was the commissioning astronomer, the senior commissioning astronomer. His wife was Rosalie Gascoigne, who was one of Australia's most noted artists. During the 1980s and 90s, she produced a huge body of work based on mostly found objects, things like road signs all keyed together make. And her work hangs in many, many significant galaxies. Sorry, not galaxies, probably galaxies as well. Galleries.
It's in one.
It's in one. Yeah, and it's a really nice thing, which always makes me think that one day the Anglo-Australian telescope, all 60 tons of it, should hang in the National Gallery as
why not?
As a work of art from Rosalie Gascoigne. Well,
they hang famous planes from various ceilings around the world.
They do. Yes, that's right. They do. Why not a famous telescope?
So, did we answer Ryan's question about why it's?
I think Ryan.
So the foam is a safety feature. Why? I think I know the answer to this, but just in case people are wondering, what causes the ice? I remember watching the Apollo launches, and you'd see ice just, falling off the rocket, the Saturn V rockets, like nobody's business. Yeah. Big chunks of it. So it's the cryogenic fuels that are used. So the stuff in the tanks,
and in that regard, the SLS, the Artemis rocket, is a more difficult challenge than the Saturn V. Saturn V's first stage used kerosene and liquid oxygen. Liquid oxygen is a temperature of about minus 200 Celsius. But the SLS uses liquid oxygen and liquid hydrogen. Liquid hydrogen is minus 253 Celsius. So very cold. If you've got a moist climate, which you do in Florida, you're going to get ice forming on it. So it's a major issue.
Yeah. All right. So it's all about safety, Ryan, and it's also a bit of a throwback to the space shuttle missions where they obviously were very keen on safety due to those couple of really sad incidents that did occur. But thanks for your question, and we look forward to the launch of Artemis 1. By the time this podcast gets out, they will have done that fuel test. But as of now, Fred and I don't know how that went. But the other problem is to do with batteries on board the Artemis 1, which ran out of certification. So whether or not they get approval to stay on the launch pad and replace, well, they can't replace them on the launch pad.
No,
they need certification to actually allow those batteries to remain in flux, if you like. If they don't get that approval, the whole thing goes back to the assembly room. So that will be a mess.
And the batteries are for the self-destruct system. It's quite interesting. Yeah. It's not, powering up the spacecraft or anything. It's all about whether you can trigger something that will basically destroy the launch vehicle if it looks as though it's going off track in any way.
Yes, indeed. All right. Good question, Ryan. Let's now head off to Cincinnati with a repeat offender named James.
Hello, Mr. Dunkley and Professor Watson. James from Cincinnati, USA, with another question. Professor Pavel Krupa of the University of Bonn in Germany published an interesting article he says disproves the existence of dark matter. Essentially, he posits that lighter galaxies orbiting heavier ones should be slowed down by Chandrasekhar dynamical friction, and that observations actually show them speeding up, as if they did not have dark matter. Professor Watson, seeing as most astronomers believe dark matter is likely to exist, what do you say to Professor Krupa's claims? Thank you both, as always, for a wonderful podcast.
Thank you, James, for that astute question. Wow. That sounds complicated.
Yeah, I think I might have misheard there. The paper that James is referring to was about the non-existence of dark matter. Was that right? Rather than definitive proof of the existence of dark matter. Maybe I misheard that. Look, it's a hot topic. It's great stuff. We had a keynote lecture at the Macquarie University Astronomy Open Night a week ago, last Saturday, given by a Sydney University professor by the name of Celine Boehm. And she basically played devil's advocate here. She put the pros and cons for dark matter or modified Newtonian dynamics or something like that, some sort of modification. I should say Peter Verweyen, our big fan and an advocate of MOND, was in the audience and very happy about the talk. So that's good. In fact, I think Celine's his supervisor for his PhD. But it was a really interesting talk in that regard because you can present fairly cogent arguments on both sides that dark matter is real, that it's some sort of subatomic particle, or that it's not, that we don't understand either gravity or dynamics properly. I find the state we're in at the moment very interesting, and pieces of evidence like the one that James has raised, and I think we may have actually covered that or something very similar to it a few weeks ago. We certainly talked about the dynamics of galaxies in multiple systems and what they tell us about dark matter. So that's a bit of evidence that suggests that it's not real. And yet there's plenty more that suggests that it is. And I think James is right. The astronomical community generally takes the view that dark matter is real. But I would say that the doubt is growing, that it is. And that's largely because despite many, many experiments and another upgrade, the Large Hadron Collider has not revealed any sign of something that could be a dark matter particle. And the things that they're looking for are candidates like axions or neutralinos, which are theoretically proposed but have not had any evidence of. So we're in a period, I suppose you could liken it to the time when the Higgs boson was predicted. I mean, it was predicted back in the 1960s by Peter Higgs, but it took until 2012 before it was finally identified. And so you've got there a pretty significant period of time, getting on for 50 years, when something was thought to be true and alternative ideas were put forward as to why subatomic particles have mass, which is what the Higgs particle does. It gives them all mass. So maybe we're in a similar limbo situation to that. There are one or two scientists who are proposing a sort of killer experiment that you might be able to do. And some of these might require a bit more time. So it is possible that we might, by a killer experiment, I mean one that definitively proves one way or the other. I suppose it's possible that we might see something like that, within the next few years. But it's a very interesting situation. So what would I say to that professor? Well, keep up the good work, because we need the arguments that if we've got it wrong, we want to know that.
I suppose it brings up an interesting point, and that is making assumptions that dark matter absolutely exists focuses everyone on finding it. But if they're wrong, then we're not looking in the right place, or not looking for the alternative.
Yes, that's right. And there is another scenario actually that maybe they're both right, because the universe is a complicated and surprising place. There might be places where dark matter is doing its thing, and other places where there isn't any dark matter for whatever reason, and modified dynamics is doing its thing. So yes, it begs the question, will we ever understand it? And my guess is yes, we will. We've tied down, it's a reminiscent, sorry to keep drawing these things out of the air, but I remember a time when there were two totally different camps in the determination of the Hubble constant, which is that parameter that tells you how fast the universe is expanding. Two values for the Hubble constant, which had very tight error bars, but one was twice as much as the other. One was 50 kilometers per second per megaparsec. The other was 100 kilometers per second per megaparsec. And guess what? The final answer that we now know is 75 kilometers per second, or thereabouts. It's almost exactly the average of them.
Yes.
Things like that work out in astrophysics, and maybe the same will happen with dark matter.
I've got a feeling when they figure it out, they'll go, "Oh, of course! Why didn't we think of that?" Has that ever happened to you in your role as an astronomer?
Look, every day. I honestly, when I look at some of the, my job now, a lot of it's just soaking in what's going on in the world of astronomy and looking at what lots and lots of different groups internationally are doing. And there are times when I think exactly that. Why didn't I think of that? That's a brilliant experiment to do. I wish I'd thought of that. And because some of these things are really quite simple and straightforward.
Well, in radio, I still haven't got past the "what's this button for" situation. Still working on that one.
Don't press it now.
No, don't touch anything.
No, don't touch anything. If it ain't broke, don't fix it.
Exactly. All right. Thanks, James. Great question. Great to hear from you. Hope all is well with the Cincinnati Bengals. I think they got off to a pretty slow start this season, but still hoping for that Super Bowl. Fingers crossed. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts with Andrew Dunkley and Professor Fred Watson.
Yes, indeed. And great to have your company, and plenty of questions to get through still, Fred. And this next one, this might be a simple one to answer. This comes from Chris, who's been outside looking up.
Hey there, my name is Chris from North Carolina, USA. Just kind of stargazing out here tonight, and came upon a star flickering white and red, which seems to be abnormal from the rest of the stars we see in the sky tonight. And looked up my phone. Seems to be Artemis or Morphid in the Bootes constellation. I'm not sure if I'm saying that right. But I was just wondering if that is an optical illusion from possibly the atmosphere, or is that effects on the light from travel through space-time on the way here, or is that just a property of the star? yeah, again, first time leaving the question here. You guys are amazing. Keep it up, guys. Love your podcast. Thanks.
Thank you, Chris. I think it's really cool that he was out observing, saw something, and thought of us. I reckon that was...
Yeah, that's great.
That's awesome.
It is awesome. Yeah, well, you came to the right place, Chris. So I didn't get where in the US Chris was.
Yeah, I couldn't quite pick it up.
Oh, never mind.
But
anyway, it's great. And it's great to have, so many people from the United States coming in with questions. So Chris has sort of already answered his own question because, and it may well have been Arcturus, which is a bright star, which could well have been fairly low on his horizon when he saw it. I'm not sure when this question came in. But flickering stars like that, that flickering is entirely due to the atmosphere of the planet. Because while stars do change in brightness, they don't do it over the timescales that we're talking about. And the stars flicker as seen from the surface of the Earth on a timescale actually measured in thousandths of a second. So it's it's a phenomenon which at the technical term, there is a technical term. We often call it twinkling, and that's that's the really nice way. But actually, the technical term is scintillation, and it's what's happening is that the light from the star, which is constant, hits the Earth's atmosphere. Which, as the light comes down through the atmosphere gets more and more dense. The atmosphere is not homogeneous. It's got warm and cold pockets of air in it. The temperature differences are not large, but they're enough to change the refractive index of the air, which means that they disturb the passage of the light. And in fact, when you get to looking at stars relatively low down on the horizon, not far above the horizon, you also get not just this the flickering, you also get the light being broken up into its spectrum colors because the air currents are almost acting like prisms that split the light up, and so you can see these flashes of red and green and blue sometimes, and it's actually something I find quite charming to watch, but it's the death knell for ground-based astronomy, because as soon as you get a big telescope looking at this, even high in the sky, the stars, you don't really notice the stars twinkling when they're, a long way from the horizon with the naked eye, but the telescopes do. And what you see, basically, first of all, the star image is waving around really quickly. It's sort of, the image itself is almost like, a moth around a flame or something like that. It's just flickering around, but it's also growing and shrinking. As the atmosphere focuses and defocuses the light as these air currents go through. And so it's a mess. It's like this sort of football where it should be a stationary point of light. If you're in space, a tiny point of light, quite stationary. But basically, it looks like this inflated blob that's not only swelling and shrinking, it's moving around. We've talked a little bit about one of the techniques astronomers use to combat this, called lucky imaging, where you can only do it for bright objects. You essentially take a video, and in those moments where the atmosphere is briefly stable, so you can see more detail, that's the image you select, and you throw most of the rest away. It's pioneered by Craig Mackay, who's an old friend at the University of Cambridge. So that's the problem as seen by astronomers. There's one addition to it, and that is when you get stars near the horizon and observe them in a big telescope, the atmosphere itself, the whole atmosphere, is acting like a giant prism. And so you get something called atmospheric dispersion, which means that instead of the star being a point of light, it's stretched into a short spectrum with red at one end and blue at the other. And that's a distortion. And if you add to that the scintillation that I was talking about, this twinkling effect, then you can understand why you can see multiple colors when you're looking with the naked eye.
So it's just simply a trick of the atmosphere.
It is. And
which is a frustration. I've actually shared that frustration when I've seen a fabulous moon rise and thought, I've got to get a photo of that. And it looks amazing to me. But then when I look at the photos, they're terrible because the telescope is affected by because I'm looking out rather than up.
Yeah.
It's going through more atmosphere, and
that's exactly right. It's going through
ruins the picture.
Thicker part of the atmosphere. One little postscript here, Andrew, is that generally, and this is, some people perhaps think this is an old folk tale, but there's truth to it. Generally, planets don't twinkle. You really need to be looking at the bigger ones, or bigger in terms of their angular diameter. Mercury does. Mercury's small enough that it behaves like a single point of light. Okay. And so you get the twinkling. But for Venus, Mars, Jupiter, Saturn, they have even though you can't see that they're a disk with the naked eye, that is the case. It is a disk. And so the light from the star follows slightly different paths through the atmosphere, and it sort of negates the twinkling. So you get a much steadier appearance, particularly with Jupiter. And Jupiter's actually in our eastern sky right now.
I was about to bring that up. It's closer than it's been in 59 years from what I've read. Yes,
that's right. It's about at opposition, and it's a close opposition. So, Jupiter's one that the atmosphere's got to work pretty hard to make Jupiter twinkle. It always has this steady light, as does Saturn as well, because that's reasonably big and bright too.
All right, I might have to dust off the telescope and see if I can get a Jupiter pic. I reckon it's worth a shot.
Indeed, it is.
Be interested to see if any of our listeners post anything on the Space Nuts podcast group on Facebook. Thanks, Chris. Let's now talk Spacetime with Tom.
Hey, guys, this is Tom in Orlando, Florida. On your most recent episode, you were talking about space-time. Somebody asked what it was made out of, and you mentioned the ether, the luminiferous ether. When I first heard of dark matter and dark energy, that's the first thing that popped into my mind was ether, that both of those are the same thing, that they're going to turn out not to exist. What do you guys think of that? Great show. Thanks.
Wow. I didn't know the substance of that question, but it certainly reflects on something we've already talked about
It does,
today.
yeah. And it puts a nice historical perspective on it because, the ether, it's a logical thing. If sound waves need the atmosphere to travel through, what is the medium that allows light waves to travel? Because 19th century scientists knew that light was a wave motion, and so the ether was what was postulated. It's an old idea actually that goes back probably to ancient times. But once you know that light is a wave motion, then it's a natural thing to say, okay, it's a wave motion. What's it a wave motion in? And the answer is nothing. And it took that classic Michelson-Morley experiment in the 1880s to determine that the ether wasn't there, because if there was an ether, the speed of light should change or should be different depending on what direction the Earth's moving in. And it wasn't. It's always the same in a vacuum. And so that kind of put the nail in the coffin of the ether, but also set the stage for both special and general relativity.
Wow. Okay. Asked and answered, Tom.
Yeah, it's a good analog, and Tom, well done. When you heard about those things, the first thing you thought of was the ether, and the fact that the ether was disproved. Well, as we've just been talking about a few minutes ago, it could be the same with dark matter, and dark energy is a slightly different one because there is clearly something driving the expansion of the universe to accelerate. So there is definitely an energy there. But none of us have really any idea what it is, what this energy of space-time is.
Yes, and that's probably a tougher nut to crack than dark matter.
It is, actually. You're absolutely right, Andrew. It is. I think it'll take us longer to work that one out than dark matter.
I'm just curious, going back to the flickering stars question and that's being caused by the atmosphere. What must the ancients have thought when they looked up at the skies and saw the colours and the flickering? And they probably would have seen more than we do because they wouldn't have had light pollution to deal with. So they would have seen they would have seen some amazing things and just stood there in wonder or maybe even fear.
Yeah,
perhaps.
I think something like the flickering or twinkling would be. They wouldn't have known it was the atmosphere. But the fact that it sort of happens every night would have reassured them that it's just part and parcel of the whole, the whole mechanism of the heavens. If it was something that suddenly hadn't happened before and suddenly did,
that's different.
Yeah, that would be different. But you're right that it was the evening's entertainment for ancient people.
Possibly so, yeah.
Yes, yeah.
Fascinating. All right. Thank you, Tom. Thank you, Chris. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
All right, we've got a few more questions to go, and the next one comes from our good old mate, Buddy in Oregon, I think. Yes, it is. It's Buddy.
Hello, Space Nuts. Buddy here from Oregon again. Hey, do they think that could black holes absorb space itself? And if it does, could that be dark matter? And then that could also be dark energy if space is expanding from itself. It's a place where the space is growing faster than the black hole is pulling it in. All right. Sorry, just a thought, guys. Big fan.
Thanks, Buddy. It looks like all these questions are dovetailing very well.
Very, very nicely, that's right.
Yeah. Black holes absorbing space itself. That's an interesting idea.
Yeah, it is. And so I'm just trying to get my head around the best sort of analogue for this, because certainly black holes do very funny things to space. In our understanding, a black hole is by definition a singularity, a point in space of infinite density. So it is actually in space, but the space around it is highly distorted, but not being sucked in. It's the stuff that's moving through the space that's being sucked in. So I think we can be fairly reassured that the geometry of space, while it is highly twisted and tortured in the region of a black hole, isn't being sucked into it. If I can put it that way. It's the stuff that's in space that's being sucked in. But it is an interesting thought. Yeah, I wouldn't like to relate that one to dark energy. It's just too hard for my brain at this time.
Fair enough. So probably no, Buddy.
Yeah,
probably a no on that one. All right. Thanks, Buddy. Now, Simon has texted us a question. He said, hi there, Space Nuts. Got a question or two for you. How fast is gravity? It takes light about 8 minutes to reach us from the sun, give or take. But if the sun would just disappear, how long would it take for Earth to lose the sun's gravity? Is it instantaneous? And how fast is magnetism when you're already answering the first question? So that's what he's asking. Have a good day. You too, Simon. I've never thought of gravity having speed.
It does. And I think we've spoken about it before. So
okay, well, I must have forgotten.
You have thought about it before. Maybe it was so traumatic you've just wiped it from your brain.
That'll do. That's a good. That's a good reason.
General relativity predicts that gravity would propagate at the speed of light, and indeed it does, because now we've got the wherewithal to measure gravitational waves. We can time the speed of a gravitational event from one LIGO detector to the other. I can't remember how far apart they are, 4,000 kilometers, I think. I think it's 3,000. And so, it's a significant amount of time that it takes for the signal to get from one to the other. And it is indeed the speed of light. So that would be the same for magnetism too, because light is an electromagnetic phenomenon. So magnetism is also part of that. So yes, everything goes at the speed of light, except space nuts.
Yes, we're a bit slow, especially me. Now, he does also ask about the sun disappearing and how quickly the gravity would disappear from our vicinity.
It'd take 8 minutes before the Earth set off in a straight line rather than being in orbit around the sun.
So if God just plucked the sun out of the sky, we'd have 8 minutes before we all
but we wouldn't know about that. We'd just see it going, and the Earth would, at the same time, just carry on in a straight line.
Yeah, and that'd be the end of that.
Well, it'd be entertaining, wouldn't it? It'd be
for a brief time until we realised what was happening.
Until we froze to death,
yes, or something like that.
Yeah.
And all the oceans floated up out of the...
Well, there's that too, yes. If we lost the Earth's gravity as well, yes. If the Earth ceased to be a gravitating object, we'd be in deep trouble.
Yeah. But if it was just the sun, we would just float off into a frozen hell.
Oblivion, yes, that's right.
Yeah, great question, Simon. Thanks for that. I've got to go to sleep tonight, That's very difficult. No, appreciate the question. Always creates... I love these what-if questions. We've got a few coming up in the next several weeks, which I'm looking forward to as well. So, yes, thank you, Simon. Now, one final question before we finish up for this episode from... I love this question simply because he will not give up on this concept. He will not let it go. He's tried twice to convince us that we could terraform Mars, and we finally convinced him that it can't be done. So he's moving on. I'm talking about Martin.
Yes.
Oh, space nuts. Martin Berman Gorvine here, writer extraordinaire in many genres, from Potomac, Maryland, USA, calling to help fill up Andrew's inbox again after his email disaster. Okay, so you guys have convinced me it's no use trying to terraform Mars. So what if we turn our tender attentions to the planet Venus? Let's say, for the sake of argument, that we could figure out a way to make the atmosphere tolerable and breathable, and bring the temperature down. What kind of problems would Venus's extraordinarily slow rotation, its day, cause if the atmosphere were able to be adjusted like that? Can't wait for the answer. Love you guys. Love your podcast. Berman Gorvine, over and out.
Thank you, Martin. Well, we already know it's a very dangerous place for lens caps.
It is.
So,
and spacecraft.
That's one important safety tip. And spacecraft, yes.
Yeah, it is. So if you had a benign atmosphere on Venus, and I suspect terraforming Venus is a non-starter, simply because it's too close to the sun. I might be wrong there because, in its history, the Earth has gone through some strange periods, like the snowball Earth period when the planet was covered in ice. And that's due to the complexities of its atmosphere. And maybe Venus has complexities too that would let you get to a snowball Venus despite where it is in relation to the sun. But yes, the fact that Venus is upside down, that's the thing. It's if you define the North Pole as that point above which a planet seems to rotate anti-clockwise, as on the Earth, then Venus is upside down and has a slow rotation that's almost but not quite tidally locked to its orbital period. So it would be a very strange world. Long days and long nights.
The Swedish would adjust well to Venus.
They'd be fine, especially the nights. The Earth is destined for a similar kind of fate when the Earth-Moon system finally stabilizes. Unfortunately, I think the Sun will have turned into a red giant star before that. But when the Earth and Moon stabilize, the Moon, the month and the day will be the same length because it will take the Moon the same time to go around the Earth as the Earth rotates. So one side of the Earth always faces the same side of the Moon.
Yeah.
Or always faces the Moon. So our day then will be about 47 of the present Earth days.
Wow.
and the moon will be 500,000 kilometres away, so it'll be a lot smaller in the sky. We won't have eclipses anymore, but neither will one side of the Earth be able to see the moon anymore, and we'll get these long days and long nights. And yes, the Swedes will love it. It'll be great.
Well, anybody up in that northern hemisphere type of area where they get those long summers and terribly long nights in winters. It's still one of my bucket list things is to go and play golf in Scandinavia at 1 o'clock in the morning or tee off at midnight, which they do.
They do,
I'm told.
Oh, they would easily.
I'd love to give it a try.
In the Arctic regions, that's right.
Yeah, that'd be fun.
It's charming, as you know. We've been many times up to northern Sweden in winter when the sun doesn't rise. And in fact, on a number of occasions, we've celebrated the first sunrise of the year. Actually, the last time I think was in Norway, in Narvik. I beg your pardon, Tromsø, where the sun just appeared over the horizon, coming back into reality.
Isn't there a time of year where it kind of bobs?
Well, it bobs in the sense that if you've got
the
horizon, the horizon makes it appear and disappear as it drifts along.
That's what I meant. I didn't mean it actually bobbed like a ping pong ball.
No, I knew that.
Yeah. Just my interpretation of the situation. But it's Venus is fascinating because its composition is it's similar size to Earth. So when we are standing on Venus, it's almost the same gravity, is it not?
Its mass is a bit different. I think the density is different. I can't remember which way it goes. But you're right. It's more or less the same. And we don't actually know. I've read papers recently that suggest that Venus may have plate tectonics because the jury's kind of been out on that for a while. There are certain geological features. Of course, you can only see them through radar because the clouds are pretty well opaque, so you can't see any details with a visible light telescope. But there are suggestions that there are some geological features on Venus that look as though there's been recent activity that could be interpreted as tectonic movement, a bit like we have on Earth. So fascinating. Great place to go.
Martin, when it comes to terraforming, never say never.
No, never say never. I look forward to reading whatever science fiction book it is that Martin's writing that's got Venus in
while
it.
I'm thinking about it, hang on.
Yep.
Martin sent me a book, and I meant to say thank you, Martin. And I think I might have mentioned it in a previous episode, but I'm looking. I'm taking a plane trip soon. I'm going to take that and read it on the plane. The Double Life by Martin Berman Gorvine.
Fabulous.
So, thank you for that. I'm looking forward to it. That'll be fun. So thanks, Martin, for sending that in. I appreciate it. And thanks for the question. As always, entertaining. And I'm waiting for your sequel Venus terraforming question. I'm sure there will be one. And then it'll work on something. It'd be Mercury next.
No, well, I was going to say, let's do the sun. Why bother?
Why not?
Why not? Why mess about with planets? Yeah,
indeed. Thank you, Martin, and everybody who contributed. And to those who've already sent questions in that you haven't heard yet, we'll get to them unless we've already answered them in some other form. Although sometimes we double up just because the topics are so very fascinating and so insightful too. We love to hear your questions. So you can send them in to us via our website, spacenutspodcast.com or spacenuts.io. You can click on the AMA link and send us a text question or an audio question there, or you can click on the tab on the right-hand side of the homepage, which basically allows you to record an audio question. As long as you've got a device with a microphone, you are set. And don't forget to leave your reviews through your favourite podcasting platform. Always helpful. Just sort of gets us noticed by people who probably would enjoy Space Nuts but didn't know we exist. So reviews are always very, very handy, and they work. I mean, we've got a growing audience, which is fantastic. And thanks for all the positive feedback too. We really appreciate it. I'm glad you're enjoying the show. And while you're on the website, while I'm spruiking, don't forget to visit the Space Nuts shop. and the Astronomy Daily tab there. And don't forget our other podcast, Astronomy Daily, which is available through our website as well. There's over 20 editions of Astronomy Daily out there already, so listen into that. I think that just about brings us to the conclusion. Fred, thank you so much.
Oh, it's a pleasure. It's great to have everybody's questions. Long may they continue. It's good to get my brain turning over again on some of these issues. So let's do it again sometime soon.
That will be great. Thanks, Fred. Fred Watson, astronomer at large, joining us every week here on Space Nuts. And from me, Andrew Dunkley, thanks for listening. Looking forward to your company in the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.